Hello everyone. So welcome to IIT and Gate classes. So this is a gas dynamics uh, video series. So today I am going to discuss about normal shock relations. So the normal shock wave is one of the important topics as far as Gate is concerned, and it is the beginning of where we can see how a compressible effects can drastically change flow environment. So that is uh, that we can see from a normal shock relations. So let us start a topic of interest today. So I'm Akshay. So your instructor for gas dynamics topics. Okay. So we already saw in the previous sessions that a compressible flow energy equations can be written in a different ways. So this is one of the form we arrived at. So where we can relate a total temperature to static temperature as a function of Mach number for calorically perfect gases, right? So what we can also do is, so we can express the energy equation in speed of sound form. So that is given by, so I have a square by gamma minus 1 plus u square by 2, which is equal to, so we imposed a unique condition that the flow is adiabatic. So for given that the flow is adiabatic, we can define a characteristic Mach number A star. So that is nothing but when flow comes to sonic condition, right? So from this way, so we define A star. So energy equation can also be written in terms of characteristic speed of sound. Also, this is a well-known form, that is using a stagnation speed of sound, the speed of sound at stagnation condition. So this is equal to constant. So this is a very important energy equation formulation, so which is useful for normal shock wave uh, properties derivation, right? Properties change across the normal shock wave. So now we now define a Mach number that is called a characteristic Mach number. So that is defined for a local speed of the flow to characteristic Mach number. What if the local flow becomes sonic? So this velocity is not equal to u star. So this is a normal flow velocity. It can be any value, whereas A star is a condition hypothetically if flow becomes sonic from U. So if U becomes U star, what happens to that flow? So what would be the speed of sound, or what would be the local velocity? It's like a sonic condition. So what is the speed of sound for a flow which is going at a speed u? So this is how the characteristic Mach number is defined. So this is why m star cannot be 1 always. So that we will see later. So where a star is defined as root of gamma r t star. This is fine. So these are the important things we have to keep in mind while moving forward. So now we will see what is the relationship between the actual Mach number to characteristic Mach number, because actual Mach number is defined as m is equal to u by a, that is a speed, local speed of the flow to local speed of sound in the flow, and m star we defined earlier. So what is the relation between that one? If flow at m becomes m star. So how they are related, right? So for a given m, what should be the m star? If the flow hypothetically becomes a sonic condition, what would be the value of m star then? So that is what we are going to calculate. So m star is now a defined quantity. So m is the actual value of the Mach number in the flows of interest. All right. So okay. So let us again come back to our energy equation, which relates uh, velocity, local flow velocity, and speed of sound locally in the flow, and characteristic speed of sound. So now what I am going to do is, like, I am dividing the equation by u square, or I am taking the u square common, whatever way it is fine, it is fine. So this gives me a unique condition that now a by u, what is a by u? That is nothing but 1 by m, right? U by a is Mach number square times 1 by gamma minus 1 plus 1 by 2 is equal to, again, gamma plus 1 divided by 2 times gamma minus 1 times a star by u, that is nothing but 1 by m star square, right? So now we expressed in terms of Mach number and characteristic Mach number. So now what I'm going to do is, like, I'm keeping m star one side and taking all other variables to other side. So how we can do is, like, so that one we can do by taking LCM. So we had a left hand side, that is 1 by m square times 1 by gamma minus 1 plus 1 by 2 is equal to gamma plus 1 divided by 2 times gamma minus 1 times 1 by m star square, right? So now if I take LCM over here, this becomes 2 plus gamma minus 1 times m square divided by 2 into gamma minus 1 times m square is equal to gamma plus 1 divided by 2 times gamma minus 1 times 1 by m star square, right? So now what I can do is, I have 2 times gamma minus 1, 2 times gamma minus 1 common in both the sides, so I can cancel out. So that gives me a relation, that is so I can take this to other side and keep m star to other side. So that gives me a condition that m star square, so I'm taking m star to other side, all other terms to this side, is equal to gamma plus 1 multiplied with m square divided by 2 plus gamma minus 1 times m square, right? So this is my relationship between m star and local Mach number m. So now from this one we can see a different ideas, right? So one is, what happens if local Mach number is 1? So if local Mach number itself sonic condition, then what happens? So if this is 1, so this becomes gamma plus 1 divided by 2 plus gamma minus 1. That again becomes gamma plus 1 by gamma plus 1. So both cancels out. So it gives, if m is equal to 1, then m star also equal to 1. Now, what if m is subsonic? So then what happens if I put the m is equal to subsonic over here? So that gives me m star also a subsonic. if M is supersonic, then M star is also supersonic. But the unique condition, can it be very high value? Say like if M tends to infinity, what happens to M star? Whether it tends to infinity, so that we will see. So what we are going to do is, we are going to apply limit M tending to infinity for M star square equation, so that we have limit M tending to infinity gamma plus 1 times M square divided by 2 plus gamma minus 1 times M square. So now if I take the M square common over here, so that's still limit M tending to infinity. So M square common, gamma plus 1 in the numerator, and in the denominator again I'm taking M square common, so that gives me 2 by M square plus gamma minus 1. So now if I apply the limit M tending to infinity, so this is getting cancelled. So this 2 by M square becomes 0, 2 by infinity. So this becomes gamma plus 1 divided by gamma minus 1. So this is interesting. As M tending to infinity, my M star square tends to gamma plus 1 by gamma minus 1, or M star is equal to square root of gamma plus 1 by gamma minus 1. So as M tend to infinity, M star tends to square root of gamma plus 1 by gamma minus 1. So it reaches a finite value. So it doesn't shoot up and goes to infinity. M star is going to be a finite value, right? Okay. So now we will see about the normal shock relation. That is the topic of interest we started off with. So till now, whatever we did, so we covered some of the basics, what we have seen in the previous sessions, that is forms of energy equations, and we arrived at a unique condition called, we derived a unique definition, that is M star, and we related M star to flow Mach number. So that is going to help us in doing the normal shock relations. So in the normal shock relations, so what we are going to take is, we are going to take a thin region, that is a normal shock, and we are going to draw a control volume that covers the normal shock. And whatever is upstream to this one, we call it as state 1, and whatever is downstream to that one, we call it as state 2. So from here we will from here onwards we will do the uh, analysis. Okay, so what are the assumptions we are going to take when we derive the normal shock relations? One is, we are treating this flow to be steady, and we are treating this is one dimensional, and we are treating inviscid or frictionless only during the control volume analysis. Why? Because we are treating normal shock within the control volume, and we are not going to open the black box. So control volume analysis all cares about what comes in and what goes out. What's happening inside, it is not our interest. So that is why we are treating it as an inviscid and frictionless for the control volume analysis. But in normal, what is the case is, the normal shock itself is a very thin region where large amount of viscous dissipation can happen. So the normal shock wave is the shock itself is a viscous phenomenon. But for a control volume analysis, we are not going to take it as a viscous phenomenon. So what we, and also there is a large amount of heat transfer within that thin region that happens in an actual scenario. But the case what we are going to consider is, so we will treating it as across the normal shock wave flow is the adiabatic. Across the normal shock wave flow is adiabatic. That is important. And we have no body forces involved in the control volume analysis. Okay, so keeping these things in mind, so now we are going to try find out what is the property change across the normal shock wave, and can it be expressed as a single function? If I know the upstream properties like pressure, temperature, density, Mach number, or speed of sound, or velocity of the fluid, and stagnation properties, if I know this condition, can I calculate the downstream condition once the flow passes through the normal shock wave? That is the question we are going to address now. And can I express it as a single function, single variable functions? So that is the other question we are going to address. Okay, so let us start this one. So we have three governing equations given by continuity, momentum, and energy. So the one-dimensional continuity equation, we have 1D continuity. So that gives both relative velocity and actual flow velocity are on the same direction. So that gives me minus rho1 u1 a1 plus, that's just the mass flux, a2 is equal to 0, or if I take the other side, it becomes rho1 u1 a1 is equal to rho2 u2 a2, and we are taking the control volume such that both entry and exit areas are same, so that can be cancelled out. So that gives me the continuity equation rho1 u1 is equal to rho2 u2. And this is important relation. So now we have a momentum. So for 1D momentum, the equation turns out the pressure forces, that is P1A1 plus rho1 U1 square A1 is equal to P2A2 plus rho2 U2 square times A2. So now again A1 and A2 are same, so I can cancel that area which is multiplying and express in terms of per unit area. That becomes P1 plus rho1 U1 square is equal to P2 plus rho2 U2 square. And not deriving everything from a basic control volume analysis like applying Reynolds transport theorem, because this condition we have seen in while deriving the speed of sound equation. So there we did the same thing. So we arrived at the governing equation for compressible flows and 1D momentum and continuity equations. So that's the same, the derivation remains same. But important thing here is like, what are my governing equations? And I have a energy equation. Energy equation is straightforward. So this one we have solved multiple times. So that is nothing but h1 plus u1 square by 2 is equal to h2 plus u2 square by 2. So this is my energy equation. And now I have totally 5 variables, that is density, velocity, pressure, temperature, and enthalpy. So now I have to solve, but I have only 3 equations. So that is not sufficient. So what we are going to do here is, we are going to use the other relation, that is H is equal to CPT. What is this one? This is enthalpy relation, right? And I have other relation, that is P is equal to rho RT. So that is the equation of state. So we are going to introduce these two new relations. So now we can address for the unknowns. So these are my governing equations for a normal shock, and we can now go on and address the property change across the normal shock. So let us see the first one. So that is trying to relate the upstream Mach number and downstream Mach number. So given the upstream Mach number, can I calculate the downstream Mach number? So that part we are going to address now. Okay. Okay. So I had momentum equation, that is P1 plus rho1 u1 square, which is also equal to P2 plus rho2 u2 square. So that is the momentum equation. And if I divide the whole equation by continuity equation, so that is nothing but rho1 u1 is equal to rho2 u2. So if I divide this equation by this equation, so that turns out P1 plus rho1 u1 square divided by rho1 u1 is equal to P2 plus rho2 u2 square divided by rho2 u2. Okay, so now what happens? P1 by rho1 u1 plus rho1 u1 square by rho1 u1, that only gives me u1 is equal to P2 by rho2 u2 plus u2. Okay, so here is an interesting uh, part. So what is P1 by rho1? So I have a speed of sound. I have a speed of sound which is given by root of gamma p by rho. So this is what we derived while discussing the speed of sound. So if I write like this, a square by gamma, which is also equal to p by rho, right? So I can replace like that. So if I do that, what happens? So this becomes a1 square divided by gamma times u1 plus u1 is equal to a2 square divided by gamma times u2 plus u2. So now I am taking the terms which is having speed of sound one side and the velocity to other side. So that gives me a1 square divided by gamma u1 minus k2 square divided by gamma u2 equal to u2 minus u1. Right? So this is an interesting relation we got now. So now what we can do? So now I had the relation for energy equation that is given by a square by gamma minus 1 plus u square by 2 is equal to gamma plus 1 times a star square divided by 2 times gamma minus 1. So now I'm going to use this condition to define what is a square. So how I can write a square? So I can write a square by gamma minus 1 is equal to gamma plus 1 times a star square divided by 2 times gamma minus 1 minus u square by 2. And if I just keep a square this side, so that becomes a square is equal to gamma minus 1 cancels. So that becomes gamma plus 1 times a star square divided by 2 minus gamma minus 1 by 2 times u square. Right? So I can replace like that. So I am going to do the same in this equation. So I am going to replace A1 square and A2 square using the energy equation. So expressing in terms of A star square. And we know for an adiabatic flow field, A star is constant. So I can use that A star to be same in both the conditions. So that is, we are talking about upstream of the normal shock wave and downstream of the normal shock wave. So now what I'm having is, so let me write it. Yeah, 1 by gamma u1 times a1 square. So that a1 square I am replacing in terms of a star square times gamma plus 1 divided by 2 minus u1 square times gamma minus 1 divided by 2. Similarly, I had 1 by gamma u2 times a star square times gamma plus 1 divided by 2 minus u2 square times gamma minus 1 divided by 2. So which is equal to right hand side, that is u2 minus u1. Okay. Now it looks a very long expression, but luckily we can simplify this one. So that is 1 by gamma u1 times gamma plus 1 by 2 times a star square. So I'll write here a star square minus, so this u1 and if I take this inside, so 1 u1 get cancelled, so that remains u1 times gamma minus 1 divided by 2 times gamma, right? Similarly, the other side, minus a star square times gamma plus 1 divided by 2 times gamma u2 minus of minus, that is plus u2 times gamma minus 1 divided by 2 gamma, which is equal to u2 minus u1, right? So now, keeping this a star square one side, so that means like taking a star square common and divided by 2 gamma, that is common. So that also gamma plus 1. So these things we can take common. So what we left with 1 by u1 minus 1 by u2. So the other one is plus, I can take gamma minus 1 by 2 gamma common. So that gives me gamma minus 1 by 2 gamma times u2 minus u1 equal to u2 minus u1. So if I take LCM here, so what happens? So that gives me a star square times gamma plus 1 divided by 2 gamma times u2 minus u1 divided by u1 u2 plus gamma minus 1 divided by 2 gamma times u2 minus u1 is equal to u2 minus u1. So now you see this u2 minus u1 is common in all three terms. So what I can do, I can take that as common and it cancels out from LHS to RHS, right? So now we left with, a star square times gamma plus 1 divided by 2 gamma times u1 u2 plus gamma minus 1 divided by 2 gamma, which is equal to 1. Or This 2 gamma is common, so I can take to other side. A star square times gamma plus 1 divided by u1 u2 plus gamma minus 1 is equal to 2 gamma, and take to other side. So this gives me A star square times gamma plus 1 divided by u1 u2 is equal to 2 gamma minus gamma plus 1, that is gamma plus 1. So what happens? I can easily cancel this one and this one, right? So now I left with a very unique condition, that is A star square is equal to u1 u2. And what I can do, I can keep this 1 here and I can divide A star square in this equation. That becomes A star times u2 by A star. So I'm splitting A star square into A star and A star. So what is this one? So we define m star, that is equal to 1 by, sorry, u by A star. So this is nothing but m1 star, this is nothing but m2 star. So this gives me 1 is equal to m1 star times m2 star. This is very important relation, intermediate relation we actually obtained by deriving. So this helps us in finding out the relationship between the Mach number upstream to downstream. So how we can do that? So now we got the condition m2 star is equal to 1 by m1 star, or I can also write m2 star square is equal to 1 by m1 star square, and I have the relation for m2 star square relating the Mach number locally. So that gives me gamma plus 1 times m2 square divided by 2 plus gamma minus 1 times m2 square, which is also equal to 1 by m1 star. So that turns out 2 plus gamma minus 1 times m1 square divided by gamma plus 1 times m1 square. So now we have to simplify so that we can relate m2 as a function of m1. So to do so, what happens to this one? That becomes gamma plus 1 whole square times m2 square times m1 square, which is equal to 2 plus gamma minus 1 times m1 square. So what I'm doing here, I'm just doing the cross multiplication. So to this side and to this side, that's it. So times 2 plus gamma minus 1 times m2 square. So now this one is, let us keep like this, m2 square times m1 times square gamma plus 1 whole square. This is equal to 2 to the 4 plus 2 into gamma minus 1 times m1 square plus 2 into gamma minus 1 times m2 square plus gamma minus 1 whole square times m1 square m2 square. So now interestingly, m2 square m1 square can be taken common. So if I take that one, m2 square times m1 square common, that leaves me gamma plus 1 square minus gamma minus 1 square whole square equal to 4 plus 2 times gamma minus 1 times m1 square plus 2 times gamma minus 1 times m2 square. So what is this one? This is a plus b whole square minus a minus b whole square form. So that should give me 4ab. So that is m2 square times m1 square is equal to 4 times gamma times 1. So 4 gamma, right? Equal to, again, 4 plus 2 times gamma minus 1 times m1 square plus 2 times gamma minus 1 times m2 square. So now take this m2 square other side. So I can take m2 square common. So m2 square common. So that gives me 4 gamma times m1 square minus 2 times gamma minus 1 equal to 4 plus 2 times gamma minus 1 times m1 square. Very interesting. So we can see that now m2 square is separate and all the terms which has m1 square are separate. So I can easily write m2 square is equal to 4 plus 2 times gamma minus 1 times m1 square whole divided by 4 times gamma m1 square minus 2 times gamma minus 1. So I can take 2 common in this equation. So that gives me m2 square is equal to 2 plus gamma minus 1 m1 square divided by 2 times gamma m1 square minus gamma minus 1. Sometimes what people do is, so they can write in terms of well-known relation, that is 1 plus gamma minus 1 by 2 times m square form. So to do that, so I can take 2 common now. So that gives me m2 square is equal to 1 plus gamma minus 1 divided by 2 times m1 square divided by gamma m1 square minus gamma minus 1 divided by 2. Or so it is important to remember this is relating m2 square to m1 square, not m2 is equal to in terms of m1 square. If you want to calculate a m2, that is the case usually, then you have to take the square root of this equation, right? So this is the relation that relates upstream Mach number to a downstream Mach number. Now see, m2 is a function of m1 only. So given that the given gas is calorically perfect and gamma is constant, so that is not uh, taken into account. So we are treating it as constant. But here you can see m2 is a function of m1 only. Similarly here, you see, if m1 is greater than 1, so I will get m2 is also m2 is subsonic. So this is important. So for m1 that is supersonic, so m2 will be subsonic. So the flow will be subsonic behind the normal shock wave. And for m1 is equal to 1, I will get m2 also equal to 1. That is fine. That is a weak solution. That's the weak normal shock wave. That means uh, the Mach number stays the same. But interestingly, so can I again, like I'm going to see if m1 tends to infinity, what happens to m2? So that again, if I apply the limit to this equation, so if I take m1 square common, limit m1 tending to infinity, if I take m1 square common in the this one numerator, that becomes 1 plus m square times gamma minus 1 divided by 2 divided by, again I can take m1 square common from the denominator, so that becomes gamma minus 1 divided by 2 times m1 square. So if I apply the limit, so what happens? This tends to 0 and this tends to 0. This leaves me m2 square tending to gamma minus 1 divided by 2 gamma, or m2 tends to square root of gamma minus 1 divided by 2 gamma. So this tends to a finite number again. So for gamma is equal to 1.4, that is for air, you can calculate m2 to be 0.378. That is fine. For gamma is equal to 1.4, m2 tends to 0.378. The finite number, that is important. It tends to a finite value. So it cannot go to a 0. It will go to some finite value. That is interesting. So this relates a downstream Mach number with the upstream Mach number. Similarly, we can go on and see how the other properties are related, like that is of our interest now. How pressure changes across the shock wave, how density changes across the shock wave, how temperature changes across the shock wave. Those things are important. So we are going to see that one in the next part. Okay.